Well, hi there, everyone. Thank you for signing in. It's good seeing that many of you are able to catch this live session. But do remember, if you're having any connectivity issues, if you have something happening at home preventing you from being here live while I'm working on this problem set, I am recording this whole session. It will also be posted to YouTube with a link on D2L. So if you, for whatever reason, aren't able to stick around, you can access the same content again later. That's not going to be a problem for anyone, I hope. To give you an idea of how I plan on structuring these sessions, the Tuesday, Thursday live ones, it is my intention to structure them in such a way that it assumes you've already had an opportunity to watch the video I posted yesterday. So the video discusses a lot of the theory. Hopefully I managed to contextualize that enough that there was a little bit of worked example in there to illustrate the important concepts. But then the examples we'll look at today are really meant to dig in and emphasize how problem solving works, specifically in section 13.1 today. So you'll see I have a document open here in front of me. It has 4 example problems on it. This was uploaded to D2L earlier today, and I will consistently be doing that each Tuesday, Thursday. I'll upload the example problem set to D2L if you want to reference it beforehand. But then to give you an idea of how I'll be working in class, I've created a separate document here where on each page I have one of these problems. And so this is the screen you'll see most of the time, one example problem, and I'll have a worked solution below that. And once I've finished the session today, I will save this document as a PDF and also upload that to D2L. So you should be able to look at the worked example problems and go from there. But before I jump in with these examples, does anyone at the moment have a specific question about class and about structure? I know if you're on a computer and you want to ask a question, you should be able to do that by pressing and holding down spacebar. That'll unmute you if you have a question. So I'll give a few seconds here if anyone has something they want to ask before I start working on examples. Okay, so I have a question here about quizzes. What will happen with the quizzes is on Thursday, I will, after our live session, I will release a document on D2L. You will have 24 hours within which you can take that quiz. The only provision is I'll be able to see at what point you access that file. And so you will have 1 hour from the time that you access it to complete the quiz. You'll be writing your solutions on paper, and you should get some kind of app. I'll make a recommendation on the first quiz that I send out. I use an app called TurboScan, which takes a picture of a document, identifies the edges of the page, very nicely converts it to a PDF, and you will upload that within 1 hour of you starting the quiz. But you'll have a whole 24-hour window during which you can choose when you start that. And if there's anyone listening right now who maybe uses extra time that they've been allotted by TCU, if you have that kind of accommodation, that will be taken into account for how long you have to complete the quiz. Let's see. Online homework is going to be due in exactly the same way. In fact, I've already set up the first online homework assignment that will be due on Thursday. There was no homework. Well, there was a homework due for last Tuesday. I have opened that one back up. So there were only 2 or 3 people who never completed the homework from last Tuesday. That one is back open, and so you can still work on that one again, and then there is a new homework set for this current Thursday. So there are 2 homeworks, but there was nothing due for today. And then, yes, class structure. There will be videos posted on Monday and Wednesday, which covers the theory side. And Tuesday, Thursday, when you log in and we have live interactive time, we will only be working on examples. Yes, the homework from last Tuesday was on Pearson. And yes, both homeworks are now due on Thursday. So the handful of you that maybe did not do the previous homework, you still have until Thursday to complete that. And then there's a new homework concerning today's examples and yesterday's online video that'll be due on Thursday. So a lot of questions there, but I hope I answered everything satisfactorily. You can send me an email if there's anything else that you think of, and I will try to answer that as thoroughly as possible via email. But let's jump right in. So the video yesterday introduced this notion of a sampling distribution. Now, that is a name in statistics that we use to just recognize every time we take a sample and we calculate a quantity of interest in the sample, it's going to be slightly different. If I take a sample of 10 TCU students today and I ask for their GPA, and I take another sample of 10 TCU students tomorrow and I ask for their GPA, and on each day I calculate the average, I'm going to get 2 different numbers. And so each time I take a different sample, I get a different number. And so that collection of the values I can see from all the possible samples for a specific statistic, we call that a sampling distribution. And in section 13.1, we're specifically looking at estimating a proportion. So this first example says, we're looking at all US households, and we know in the population that 44% of US households buy fresh vegetables on a weekly basis. So this 44%, this is the population value. So take note here, the examples that we're doing here assume that we know what the truth is in the population. Most of the time in the real world, if you're taking a sample, you don't know what the population actually is. But here for these examples, we're going to assume that's known because it helps us then understand what we would expect to see if we take a sample. So we're saying 44% of US households buy fresh vegetables on a weekly basis. That means our value for P, the true proportion, is 0.44. And now a researcher is going to take a sample of 150 individuals, and in that sample, the researcher is going to ask people whether they buy fresh vegetables on a weekly basis or not. So what we want to understand is, in the sample that the researcher is going to take, how much deviation would we expect to see from the true value of 44%? So firstly, part A of the question says, what shape would you expect for the sampling distribution? Remember, sampling distribution, again, is just this name that we give to the collection of all possible values. And specifically, we're looking at the sample proportion here. So the researcher is going to take a sample of 150 households and then calculate what proportion in the sample buy fresh vegetables on a weekly basis. And in the video from yesterday, you would have seen we are usually going to assume that the normal model holds. So we would expect our shape to be described by the normal model. In other words, we would expect to see a bell curve. If we could observe every single possible proportion from every single possible sample, maybe a good way to think about this is I send out every single person in class and tell you, go and take a sample of 150 households. Figure out what proportion of them buy fresh vegetables on a weekly basis. Then some of you may come back with a proportion of 40%, some of you may come back with a proportion of 50%, maybe someone comes back with a proportion of only 32%. There's going to be variation. But what you'll see is if you plot all those different proportions is something that looks a whole lot like a bell curve. What do we know about this bell curve? What do we know about its mean and about its standard deviation? Well, the mean of the sampling distribution is just the mean of the bell curve. So that's asking us, where is the center of the bell curve? And the center of the bell curve is at the true population value. So the mean is the population value, and the population value in this case is the 44%. And then lastly, calculate the standard deviation of the sampling distribution. Now, we had a formula for this in the notes, sigma of p hat. And remember, p hat is just the notation that we use for the quantity calculated in our sample. In fact, I'll put in a little box here just for notation. So notationally, P on its own is the population proportion. But if you take a sample and you calculate the proportion in your sample, you're going to stick a hat over that. And so that's how we differentiate between the true value in our population and the sample value we see after taking a sample. So the formula here is square root of P times Q divided by N. And Q is just equal to 1 minus P. So in this case, 1 minus 0.44 is 0.56. So that's our value for Q. So the way we would do this calculation is we would take 0.44, multiply that by 0.56, divide all of that by the sample size, and then finally take square root. So let me do that calculation in 2 steps. Firstly, let me do 0.44 times 0.56 and divide that by 150. And here you want to keep some extra decimals. You don't want to be rounding at this point. This value I'm now taking the square root of, and I get 0.04. Here you can round maybe to 3 decimals. So this is our standard deviation. To maybe just state all of this in a different way, the mean value I can again express as a percentage, right? So I would expect to see a bell curve with a mean of 44%, and I would expect that bell curve to have a standard deviation. If I multiply this standard deviation value by 100, I can again express that as a percentage. In this case, 4.1%. So that tells me, how much variability do I expect around the true value of 44%? So anything, we've talked about 2 standard deviations either way is very typical. So 2 standard deviations here is roughly 8%. So in your sample, it would not be atypical to go 2 standard deviations above the mean, which gets you all the way to like 52%, or 2 standard deviations below the mean, which gets you to 36%. So in a sample, you could expect a proportion anywhere between 36% and 52%. Those would be very typical values if you were to go and take a sample of size 150 from this population. So I'm going to take a moment here. I see I have a couple of questions, and if anyone wants to ask a question about this example, please use this opportunity now to do so. Okay, so let's move on to our next example. In Texas, 21% of vehicles on the road are manufactured by Ford. Assume that a researcher plans to take a sample of 110 randomly selected vehicles in Texas and record the proportion that are Ford. If the normal model holds, draw the 68, 95, 99.7% bell curve for the sampling distribution of the sample proportion, and clearly indicate the values on the horizontal axis. So let's unpack the information we have here again. This 21%, that's the value for P. That's the truth of all vehicles in Texas. 21% of them are Ford. But we're not going to see all vehicles when we take a sample. We're only going to see 110 different vehicles. So we want to know, if we sample 110, what are realistic values that we would see for a sample proportion? Now, we're saying here that the normal model holds. So what we immediately know, for that normal model or for that bell curve, the mean is going to be the 21%. And the standard deviation, we have to calculate that. Again, that's that sigma of P hat, which is the square root of P times Q over N. And again, Q is 1 minus P, so 1 minus 0.21 gives us 0.79. So in this calculation, I have to take 0.21, multiply it by 0.79, divide by 110, and then take the square root of all of that. So 0.21 times 0.79 divided by 110, I get 0.001508. That keeps going. I take the square root of that, and that gives me to 3 decimals 0.039, or 3.9%. And this 0.21 that I could express as 21%. So we now want to represent this on a bell curve. So I'm drawing my bell curve. My bell curve is going to be centered at P, or at the mean value, the 21%. Then I'm going to go up by increments of 1 standard deviation. So I'm going to add 3.9%, add again 3.9% in one direction. In the other direction, I'm going to subtract 3.9%. So what I end up with is, here I have 24.9%. I add 3.9 to that again, I get 28.8%. Add 3.9 one more time, I get 32.7%. And in the opposite direction, I'm going to subtract, right? So 21 minus 3.9 gives me 17.1%. subtract 3.9 again, I get 13.2%. Subtracted one more time, I get 9.3%. So now remember, the middle two values, they represent the 68%. The next two values, they represent 95%. And the outer two values, they represent 99.7%. So practically, what does this mean? If you go and take a sample from this population, you sample 110 vehicles on the road in Texas, and you, in your sample, calculate what proportion would be Ford, then this is telling you 68% of people who do this experiment will see a value somewhere between 17.1 and 24.9%. But some people are going to be outside of this range. But 95% of values, on the other hand, will be between 13.2 and 28.8. So it just gives us bounds on what realistic values are that we would observe when doing this experiment. What the 99.7% band tells us is that it's highly unlikely that someone doing this experiment would see fewer than 9.3% of vehicles being Ford, or that they would see more than 32.7% of vehicles being Ford. Because 99.7% of all the values will be in that range. Anyone have a question about this example? This one felt a little bit more confusing. The next one I'm doing is like a very, very similar example. So we'll have one more opportunity to work through this, but I'm going to leave a few seconds if someone has a question.
On these questions, are we assuming the normal model applies?
Yeah, so the way the questions will be formulated, one of two things will be true. It will either explicitly tell you that the normal model holds, as in this example, or if I scroll back up to my previous example, it asks something about the shape. The moment it asks you about the shape, you want to be thinking bell curve, normal model. Most of the time when we're talking about sampling distributions, we are going to use the normal model as an approximation. So yeah, if you see sampling distribution, normal model should be on the forefront of your mind. Okay, let's look at example 3 here. So in Fort Worth, 82% of college students eat at Chipotle at least once a month. Assume that a researcher plans to take a sample of 53 randomly selected college students in Fort Worth and record the proportion that eat at Chipotle at least once a month. And we want to construct the same bell curve. So we know if someone were to go out and talk to every single college student in Fort Worth, then the true proportion would be 82%. But they're only going to go out and sample 53 students, so how much variability would they expect to see? Well, that's the standard deviation that we want to calculate. That tells us what's the typical deviation from the true value of 82% in our sample. Formula for that, P times Q over N square root. Q is 1 minus 0.82, which is 0.18. And I haven't emphasized this, but be careful when you're doing the sigma calculation, make sure that you are using the values in decimal form. If you're trying to multiply percentages here, you're going to get a completely wrong value. It'll be way, way off. So you can express your solution that you get as a percentage, but do the calculation in decimal form. So square root of 0.82 times 0.18 over 53. So square root of, if I do that inside calculation, I want to take square root of 0.00278. And if I now take that square root, I get 0.053 or 5.3%. So again, what this tells me is if someone goes and samples 53 college students in Fort Worth, and they ask them whether they eat at Chipotle at least once a month, then they would expect close to 82% in the sample to say, yes, they do, but the 5.3% tells us how much deviation there is in either direction, and we can visualize that with our bell curve. So we would have a bell curve centered at 82%, but then we can do standard deviations in each direction. So I would, in one direction, add 5.3% for each increment, and in the other direction, I would subtract 5.3% for each increment. So what that gives me here is 87.3%, add another 5.3%, I get 92.6, add that quantity one more time, and I get 97.9%. And in the other direction, we subtract. So 82 minus 5.3, 76.7%. Subtract it again, 71.4%, and subtract it one more time, 66.1%. So these values again now represent my middle 68%, my middle 95%, and of course the 99.7% range. So it would be highly unusual for you to get a value below 66% or a value above 98%. But you can see here, you know, even though the truth is 82%, if you go and sample 53 students, there's still a lot of variability that could be in your sample. Your sample proportion can realistically be anywhere from 66% to 98%, and that would not be atypical. So I think what's worth noting here is this formula for the standard deviation. You divide by n in this formula. So the larger your sample size, the larger the number you're dividing by, and the smaller the standard deviation becomes. That standard deviation is like the uncertainty. Smaller standard deviation means there's less uncertainty. So the way you reduce uncertainty in the real world is by increasing your sample size. Okay, I have one more example here, and then I'll leave a bit more time for questions if anyone has any. Here, we're looking at actual data from a Pew Research study in 2015, where they polled a random sample of 1,060 US teens, and they found that 56% of those teens reported going online several times a day. So here we are told p hat equals 0.56. And the question is asking, what does this mean? Remember, p hat is the sample proportion. We did a survey here, And we can observe in our sample what proportion of teens go online several times a day, but we don't know what the actual truth in the population is. So we don't know the population truth. So this p hat is the sample proportion. What does that tell us specifically? It tells us of the 1,060 teens, if we multiply by 0.56, that tells us how many in our sample go online regularly. Now, this is 593.6, but we can't have a fraction of a teenager. We're not chopping anyone in half. So round to the nearest integer, but this tells us 594 teens in the sample reported going online several times a day. So that's part A. Part B says, calculate the standard error of p hat. Now, standard error, if you watch the video, that's just a different way of saying we want to calculate the uncertainty of the sample proportion that we have. So we want to calculate the uncertainty of the sample proportion. This is kind of the equivalent of calculating the standard deviation, but standard deviation we calculate if we know the true value of p. The standard error is the same calculation, but we use p hat instead of p. So the standard error is going to be same looking formula, but now it'll be p hat q hat over n, where q hat is 1 minus p hat. So if I plug in these values, 0.56 times 0.44, and my sample size is 1,060, I'm just going to do all of this in one go. So take the square root, I get 0.015 or 1.5%. So it looks exactly like the standard deviation calculation, except p has been replaced by p hat, q has been replaced by q hat. And the reason for that is because we don't know the true value of p. In our previous examples, we were told exactly what the population looked like. In this instance, we don't have the population value, we only have the sample value, but we can use it to do the calculation. We just call it something different. We call it a standard error instead of a standard deviation. It's trying to estimate what the standard deviation is. So the standard error is an estimate of the standard deviation. And the last part here, C, asks, explain what the standard error means in the context of this situation. So I've kind of answered that already, because it's an estimate of the standard deviation, and it tells us how much variation we would expect, or how much of a difference we could typically expect between our true population value and our sample value. So our sample value is 56%. The standard error of 1.5% tells us that's kind of a typical variation between the truth and the sample value. So we would reasonably expect to be within 1.5% of the true value. But even if we use 2 standard errors, which using our bell curve, 2 standard errors means we're capturing 95% of values, right? With kind of, I'm going to throw in a word here that we haven't defined in class yet, but that we'll get around to, confidence. With 95% confidence, the true value is within 2 standard errors. So the sample value is 56%, but 2 standard errors means 3% in either direction. We're pretty sure the true value would be somewhere between 56% minus 2 standard errors, which is 53%, or 56% plus 2 standard errors, which is 59%. So we don't know exactly what the population value is, but we reasonably expect it's somewhere in this range. This is a plausible range for the population proportion. So let's see, I know I've had a few more questions come in. So I had a couple of questions here about the difference between P and P hat. And so this is just where you want to pay close attention. If information is being given to you about the full population, if I say in the population of all Fort Worth students, 25% participate in activity X. When it's about all students or about all households, if it's about the entire population, it's just P. But the moment you're calculating something based on a sample, that's when you use P hat. So the distinction is P is the truth in the population, and that's usually the thing we actually want to know. But very often we can only get the information in a sample. That's when we call it P hat. But then the standard error in that instance can help us figure out how close we are to the true population value. So I hope that helps clear up any distinction between P and P hat. And let's see. I'll talk about the quiz again in a moment, but I had a question about why I added and subtracted 2 standard errors. I could have done just 1 standard error, but remember, if I do 2 standard errors, that gives me 95% confidence from that bell curve. If I'd only done 1 standard error, I would have had 68% confidence. But the notion of confidence, you can kind of put a hold on that a little bit, because within the next 2 class units, we will start formally defining confidence, and that'll be a little bit clearer as well. But I used 2 standard errors here just to illustrate, because we know with 2 standard errors, we're capturing 95% of the plausible values. And let's see. Yeah, I think I had another question here about P hat and P. And so, yes, you just want to carefully read whether it's referring to all US teens or whether it's just referring to in a sample of teens in the US. The moment the word sample gets thrown in there, if you can clearly tell that something is being calculated from a sample, if a proportion is being calculated from a sample, then that is going to be a P hat. So what I'm going to do at this point is end the session so that I don't have too long a video I'm posting on YouTube, or just end the recording, but then I'll still take some questions if anyone has lingering questions.